The Cognitive Systems Foundation sponsors an award in honor of Herbert A. Simon, who co-founded the field of AI in the late 1950s. Together with Al Newell, he invented list processing, implemented the first running AI system, devised the earliest computer models of human problem solving, championed the notions of satisficing and heuristic decision making. The current prize celebrates progress in this tradition. One purpose is to remind the community of Simon's groundbreaking ideas about high-level processing and their potential for understanding the mind. At the same time, it recognizes the contributions of senior scientists who have built on his early work. Yes. Thank you. The Herbert A. Simon Prize for Advances in Cognitive Systems recognizes scientists who have made important and sustained contributions to understanding human and machine intelligence through the design, creation, and study of computational artifacts that exhibit high-level cognition. This declaration draws an explicit link between intelligence in humans and machines, emphasizes the importance of constructing computational artifacts, and highlights the focus on high-level cognition. The award is sponsored by the Cognitive Systems Foundation, which contributes a cash prize of $10,000. It's co-sponsored by the Herbert Simon Society, which is actually based in Italy. So the speaker today received the award in late 2022. Let me just review a little bit about his career. This is Kurt VanLehn. He received his PhD from MIT in 1983. He worked with Patrick Winston and John Seely Brown. Spent a number of years at Xerox PARC. Later served on the faculty at Carnegie Mellon University and the University of Pittsburgh in the Learning, Research, and Development Center, before he moved to Arizona State University in 2008, where I helped recruit him. He serves there still as professor of computer science, and Diane and Gary Tooker Chair for Effective Education in Science, Technology, Engineering, and Math. Let me just read you the award statement, and then I'll turn it over to Kurt. So the recipient of the 2022 Herbert A. Simon Prize for Advances in Cognitive Systems is Kurt VanLehn for his insightful analyses of student errors, his computational accounts of human problem solving, explanation, and learning, and his development and evaluation of intelligent tutoring systems. And I believe he's going to tell us a little bit more about the trajectory of those ideas.
Great, thank you. Great. Okay. You can see that's what we're going to talk about today in this talk. Not all education. I'm basically interested in a particular issue, which is math modeling. How do you get kids to construct math models? That's where you take some kind of a situation and you turn it into a set of equations. So this is fundamentally important. In fact, it's recognized in the United States as one of 8 key practices for math and 8 key practices for science as well. So examples of that I will talk about today are an algebra word problem, physiology, physics, probability, and system dynamics. All of these are examples of constructing math models. So there's a common cognitive framework for math model construction that was first articulated by the prized Herbert Simon, 78, but he didn't name it. It was later formalized by Joe Larkin and him in 1980. It's now widely believed and used in both AI and the learning sciences, and it still doesn't have a name. So what is it? The cognitive framework assumes that people learn equation schemas. That's the key idea, which have a generic equation in them, such as distance equals rate times time, conditions for when to apply it, slots that need to be filled, and maybe a name, such as Newton's first law or distance, rate, time. And then they also have cues for when to, for recognizing when it's a good time to consider applying it. It also assumes that in the same language, the same representational language, there are soughts and givens in a problem. So here's an example. Why don't you just solve that in your head for a second? Okay, you probably recognize that the first schema application is the one I just mentioned, distance, rate, time. Now, the way this works in the framework is you fill a description slot, in this case with Zach's running, just in case there's multiple applications of the same schema and you have to tell them apart. And you fill the rate slot with 3 meters per second, the time slot with 500 seconds. You fill because there is no mention of a distance in these problem statements, you fill the distance slot with a new variable. Write down the equation, and now you apply a second schema, round trip distance, which is that the distance of a round trip is twice the distance apart of the two objects. Start the source and destination. So again, you fill a description slot, fill the round trip slot with D, which was the variable defined earlier, and fill the distance apart slot with D2, which is the new variable. Now you write the equation. Now you check for solvability. You have two equations, you have two unknowns, and then you check to see whether the slot is included. And yes, it's included, and it's D2. So that's where the cognition stops. We assume that there's some kind of calculator, like a TI-35, that you can hand this set of equations over to, and it will solve it. Okay, so we're only interested in setting up the equations, not solving them. So let's name this widely adopted framework, what's called the equation schema framework. And much of the research, especially in psychology, is on recognizing when particular schemas are useful. There isn't very much research on the slot filling aspect of it. Now recall that here's the algorithm for slot filling. So you start with, oops, wrong button. You start with if the slot matches a given, then you fill it with the given's value. If the slot matches an existing variable, fill it with the variable's name. That's the part that's not right. Otherwise, define a new variable and name it. So it turns out that this matches concept is kind of problematic for students. So here's an example of the first major issue. Many equation schemas that are used in all those domains that I mentioned are not taught. So physics makes a big deal out of Newton's law and some other things, but it doesn't teach you that the tension in a rope is equal to the magnitude of the force of the on the block caused by the rope that's attached to it. Okay. So that's just not taught. So how do people learn those things? So in order to make sure that the equation schema was not something completely out of whack with what people actually do, Cascade, which was a project done with Randy Jones, was created to both uncover how people learn these untaught schemas and to make a concrete model of the equation schema framework. So we got our data from Micheline Chi's landmark study of self-explanation, which involved 9 university students who were started by reading a physics textbook, first 5 chapters. And then they studied 3 examples from the textbook, but they are instructed to speak aloud, think aloud. Then they solved 14 problems, also thinking aloud. And during that time, they were allowed to, and often did, refer to the examples, but they had no tutoring or anything. So they often made mistakes that went undetected. And all that speaking aloud generated approximately 3,000 pages of transcript. So a lot of verbal data. That's what we wanted to make Cascade consistent with. Okay. So its initial state, first we had Cascade. We developed Cascade by basically making it a thing that could explain all the equations and lines that it saw in the examples, and then we made it, equipped it with knowledge to solve all the problems. Most of the schemas that we had to add to it were taught, I'm sorry, most of the schemas were taught, but 9 of them were not taught. Okay, so the question is, what happened when the humans hit occasions when one of those 9 untaught schemas had to be applied? So the assumption is that during example studying, a really good student would take that as an opportunity to learn something new. And it would do that by specializing overgeneralizations, such as if 2 things are kind of related to each other, then they're probably equal. Poor students would just essentially slack off. They would not explain the line. During problem solving, there wasn't an ability really to slack off, so they would copy from the examples instead. Okay, and we had a nice model of specializing over generalizations, but I won't go into that here. So in order to validate that, we want to show that Cascade and people were essentially doing the same thing, and that's a two-sided proposition. First, we have to see whether or not the stuff that Cascade does is what people do. So we basically, Cascade is a problem solver. It has lots of goals, and so we basically say which of those goals were also achieved by the person and which were unique to Cascade. And we had to, in that case, sort of tell Cascade to do something different than it wanted to do. Most of the time that involved telling it to go to refer to the examples when in fact it had the knowledge to not refer to the examples. And you could see from the Venn diagram that a huge number of the goals that Cascade did were also done by people, or seemed to be done. Okay. Validation 2. Look at it from the other side. We didn't want to analyze all 3,000 pages of the transcript, so we just picked 4 representative ones. We encoded each utterance that the persons in those transcripts uttered into inferences. And then we determined whether they were matched by Cascade. And as you can see, most of them were. So the match between its behavior and the student's behavior was pretty good. That allows us to answer the key question of what happened when the humans hit the times when an untaught piece of untaught schema was necessary. So during example study, there are 162 opportunities to apply an untaught schema. Most of those cases, the students made no visible attempt to explain the line. So they just kind of slacked off. There were 12 cases where they visibly applied, they seemed to learn. They paused, they reflected, they spoke about being confused, and then they kind of resolved it. In 4 cases, they had applied some learning, and then I won't go through the whole slide. It's a long slide, but the basic point is that there were a lot of cases where they could learn, they didn't. So what Cascade provided is a cognitive system that could learn untaught physics knowledge, okay? It also was a model of the process underlying the self-explanation effect, which is the more lines in an example you explain, the more you learn. And the benefits and harms of looking back at the example and doing an analogy. So this kind of also resolved the issue of is the equation schema framework consistent with human behaviors when there are untaught schemas? Looks like it can be extended to do that. So our first transition slide is we now understand how untaught schemas are learned or not from existing instruction. And the question then is, since I was primarily interested in education, is how can we create better instruction? In particular, when students have an opportunity to learn an untaught schema, how can we help them learn rather than just slack it off by not explaining the example or by referring to an example instead of trying to figure out how to solve a problem? So to do that, we have to monitor the students' work very closely in order to detect what schema applications they're doing and what times they get stuck. So that's called a step-based tutoring system. A step is an observable manifestation of applying a schema. For problem solving, in our domains, a step is writing the equation or some other thing like a vector. In problem solving, there's really no visible sign of the step unless you have verbal protocols. So a step-based tutoring system detects each step as it's made and determines if this step is correct, and if not, decides whether to say something, negative feedback, later, now, or not at all. So an example, the first step-based tutoring system I want to talk about is Andes. This is done with Christina Canati and many other people. It was designed to help U.S. Naval Academy students do their homework, physics problem-solving homework. It didn't have anything to do with explaining examples. Now, it was designed so that the user interface was as close as possible to paper, because the midterm exams that the people took were done on paper, and they were graded by showing the work that the students wrote on the paper. Okay. It gave immediate feedback by coloring things red if they're incorrect and green if they're correct. And there was always a help button available in case the students didn't like the red feedback. So here's what the user interface looked like. This student is solving a physics problem. You can see that most of the stuff on the right in green is correct things the students did. But there's one red equation, which is boxed because the student selected it and asked for help on it. So that's a step-based tutoring system. Andes 3's knowledge covered most of a 2-semester college physics class, all the way up to electricity and magnetism, but not covering modern. So there are 1,200 schemas, most of which were untaught. Students could write any equation, but Andes students typically never wrote a single schema application equation. Instead, they almost always wrote equations that were a combination of schemas. They kind of solved the problem as they were going along. So we evaluated Andes with a full semester of intro physics course at the U.S. Naval Academy over 4 years. The experimental classes, there were lots of these classes, so they divided them up. Experimental classes did their homework on Andes. The control classes did their homework on paper. And all the classes took exactly the same midterm exams and the same final. Here's the midterm exam results. The Andes tutoring system for homework clearly caused the students to perform better on the midterms. Okay, very clearly. Effect size was 0.61. For the final examinations in the last year that Andes was used, also Andes was a winner. Now, here's a scatter plot of GPA on the horizontal axis and the Z-score on the exam scores on the vertical axis. The black line is Andes students. That's the regression line for them. And you can see it's above the regression line for the purple for the control students. Now we're hoping that those lines would not be parallel. We're hoping that the left side of the purple line would come up and be close to the Andes line, but it didn't. So although Andes was effective, and that's great, it didn't help the poor students catch up with the good students, which is what every educator wants. So somehow, if we thought, well, if we could guide the poor students more strongly, maybe they would learn more. So we'll actually step them through the whole process of applying a schema. We had a new tutoring system called Pyrenees. It actually required students to they could not just write any equation they wanted. They first had to select a schema, fill its slots, and then they could write the equation. That turned out to be much more effective than Andes. So this is a complicated graph here, but the point is that the red line, the low students on Pyrenees, rose to be as effective as the high students on Pyrenees, which is what we wanted. Moreover, it turns out what they did on Pyrenees transferred to when everybody was using Andes. They retained their ability to learn well. So we had two more tutoring systems, Dragoon, which was a step-based tutoring system for math models of dynamic systems, and Topomath, which was a step-based tutoring system for algebra word problems. Both required students to select a schema and fill its slots, and both were more effective than conventional instruction. So what have we learned so far? The equation schema framework started by Simon is explicit in the cascade model of human studying, so seems pretty valid. And underlay the math, the Andes tutoring system, but it looks like its benefits of Andes were mostly due to a step-based framework, feedback in particular. And we also learned that teaching students to slow down, fill the slots before writing the equations was even more effective than Andes. But when we look closely at those graphs that I showed you of the students, there are always a few poor students who did, few students sort of on the left end who did poorly. So we didn't help everybody. So that became a new focus. So we started these things called algebra word problem boot camps. And this was with John Wetzel and two math instructors. So at ASU, the lowest math course offered is called college algebra. And it's essentially the equivalent of high school algebra, which is normally taught in the second year of high school in the United States. So really low level math. Most of it on waste of time, in my opinion, is about how to solve equations. Like here's an equation in one variable, how do you solve it? That can be done in a calculator, but they're still teaching it. There was, however, a sizable number of algebra word problems, and the instructors hated those, and the students hated those because they were just really difficult. So the boot camp was open to anybody in the course who was failing it. Okay. We had a handful of students. They were tutored by the two instructors and by us. And we did that to try and find some way to help these folks get through algebra word problems, really sort of get it. Because I must say, you know, for me and probably everybody in this room, creating a math model, like solving an algebra word problem is easy. It's so easy we can't figure out why it could ever be hard to anybody. So we were trying to figure out why it was hard for these students. So we're working mostly on paper. We required the students to select schemas and fill slots before writing equations, and that sort of helped a little bit. The real problem, though, was they just couldn't figure out how to handle a problem that had more than one schema in it. That was really difficult for them. Now, I'm about to reveal why that was difficult, but let me remind you, the procedure for filling a slot in the equation schema framework is if the slot matches a given, fill the slot with a given value. If the slot matches an existing variable, fill the slot with the variable's name. Otherwise, create a new variable. Okay, I've been teaching that procedure in Pyrenees, in Topomath, in Dragoon. You'd think I ought to understand that. But finally, one articulate student whom I was tutoring said, sharing variables between schema applications just didn't make any sense to her. How could a variable that denotes one slot be used to denote another slot? So slot descriptions didn't match exactly, but you're supposed to use the same variable for them? Well, how sloppy a match is allowed? She just didn't know the rule. So here's an example, a little more substantive word problem. The best I can do for helping you understand the problem from her perspective. So try solving this one. Just think of the equations you would have to write down. Okay, you're probably well done with this. So this is probably kind of what you came up with. You said, okay, the plane's flying at full speed, so I need a distance rate time for that. So that's in red here. And the missile flies at its full speed, so I need a distance rate time for that too, and that's in blue here. You might have said, okay, when it says assume the missile travels at 6 seconds less than the plane, you might have thought, okay, I need a subtraction equation for that, and that's in green. But the untaught idea here, represented by the sharing of D across the two equations, is that when the missile overtakes the plane, then the distances are the same. But if you visualize the actual situation, the missile and the plane did not follow the same trajectory. Why would you assume that their distances are the same? Well, certainly the slots are referring to two different trajectories. missile's trajectory and the plane's trajectory. So, but we're going to use D for both of those. That's what confused the student. So we revised the equation schema framework just for the sake of confused learners, you might say. So to fill slots of schemas, when a quantity slot with matches exactly an existing variable, then it's okay to use the variable. Otherwise, create a new variable and name it after the slot, because now slots and variables are in a one-to-one correspondence. An exception is that if two variables almost match, like the two distances we saw, and common sense justifies that their variables should be close, or you're just desperate to solve these system equations, then write that they are equal. Okay, so that when you don't have an exact match. So here's that problem done correctly. Okay, we got we replaced the two D's on the left side of the red and the blue equation with their own variables, and then we added a purple equality equation at the bottom. So now every slot has its own variable. Now I might add, it says, how long will it take the missile to catch up with the plane? Okay, so that can be interpreted as the time of the missile's flight. And that's an exact match to the green T missile variable. So there is a SOT here that matches exactly. So we created a new tutoring system at the very tail end of this research grant. It was a step-based tutoring system, and it was done in a big rush, 4 months. So it's not quite right. It's intended to force students to follow that revised program that I mentioned. And it's called OMRAT, which is an acronym for One Math Relationship at a Time. Okay, this is what it looks like. It's kind of a mess, but each one of those lines is a schema application. And most of the boxes are green because they filled in things correctly. One is wrong there down at the bottom, so that's incorrect. Students get 2 chances to fill in things that are wrong, and then it's filled in for them, and that's the yellow one here. It turns yellow. I won't go through everything on here. So we used this in an ASU class that I taught on math modeling. In that class, taught over many years, I always found that I first didn't have algebra word problems in the class at all because I thought everybody knew how to do those. And I discovered over the years that no, even ASU juniors in engineering often can't solve algebra word problems, which is sort of a shock. So the first module in that class was always, well, not always, but became algebra word problems. And in order to prevent students from using numerical ways of solving the problem, like guess and check and other ones, they had to do their work on something we called the solver, which was simply an app which accepted any set of equations and tried to solve it, but you could only put a number into the equation if the number appeared in the gibbons. And that prevented those numerical strategies. So in this experiment, the students did a pre-test on the solver, and we used what's called a regression discontinuity design, often used in medicine. So students above the median don't have to take the treatment. Students below the median do take the treatment, median in the pretest. And the treatment in this case was a 60-page Canvas sort of mini 2-week lesson. Had a lot of OMRAT problems, a few solver problems. And then they took everybody took the same mid-test, both the people who had no treatment and those who had a treatment. And then there were some more, in order to make everybody learn something, there were harder word problems in a post-test. So just looking at the difference between the pretest and the mid-test, again, you're looking at a graph where the pretest score is on the horizontal and the mid-test score is on the vertical. The blue folks are the treatment folks, and they're all left of the median. And the red folks are the people who didn't get any treatment. And if you run a little regression line through the blue dots, that's a hard to see blue dotted line. It's a different regression line than the red one, which is the regression line for the red folks. And there's a discontinuity at the median between the blue line and the red line. And the higher that discontinuity, the more effect you have. The regression discontinuity design. So we had a fairly large positive effect, but it wasn't, there was so much scatter in the data that it was not reliable. In other words, if you took the regression line for everybody, which is that long green one, that wasn't different enough from the other two regression lines to make for to be reliable. So encouraging result, but not slam dunk. So we repeated the experiment next year using by creating a second tutoring system, which was totally conventional, had nothing to do with filling slots and so forth, and compared that to OMRAT. And this time, OMRAT really beat the conventional tutoring system, real slam dunk. So future work is, now that we figured out how to teach these students who have a really hard time with algebra by extending the equation schema framework, we need to get them back up to the place where they can solve things without all that help, without all that scaffolding. So to do that, you fade the scaffolding, as we said. So numbered here on the left are the various kinds of scaffolding. So first kind of scaffolding was require an exact matching of slots to share a variable, and we want to take that off and allow sloppy matching, just like in Topomath and Dragoon. Then after they become expert at that, then we've, you can see we fade out the other scaffolds. So I think that'll work, but we haven't built the thing yet. It's a nasty piece of software to build. So the summary is, the equation schema framework has enabled a lot of cognitive systems not covered here, and tutoring systems such as the ones covered here. An extension is recognizing that variables should be shared between schema slots only if the slots match exactly, and then you use an equality schema. So the reason why nobody noticed that is we're all used to basically taking two or more schema applications and sort of combining them in our heads and only writing one equation. So that comes later for these poor students. You have to teach them that first you break the thing apart into two, and then they can later merge it in their heads. So I haven't really shown you this, but there's a lot of data showing that step-based tutoring is good, and a lot of data showing that fading is good. Okay, so that's what I have. Thank you for listening. Questions? Where's that microphone?
Thanks for the talk. I'm always curious with educational interventions like this. Did the students like it? Like, how is engagement?
I'm glad you asked that question. There have been countless studies in education which have shown that stuff that is educationally more effective is almost always not liked by students. And I'll go beyond that, which is, for example, lecture, which is known to be the least effective ways for teaching college students, compared to having them flip classrooms where you have them do reading at home, and then in work do they problem solving in class and discussions. Ask them which one they learned more in. They said, "Oh, I learned a lot more in lecture," but they're they do poorly on tests. So if you ask me, what would be an easy way to evaluate a system if you don't want to do the whole post-testing thing, is just ask whether the students like it, and if they don't, then it's a good system.
I don't remember whether it was Kate Balachik or Mimi Record that had looked at, they had people that were studying or doing problems, and had talk aloud protocols. And then there was this gap between sessions of problems. That old computer had to be reloaded, but they found that some of the students would still be in the mode of talking and the recorder was still on. And they found that good learners happen to talk more about and try to analyze their own problem solving. It was kind of similar to Chi's self-explanation effect. And I expected to hear a little bit about that. As far as an intervention, is that not effective to have students perform some kind of thinking about their own problem solving and talking out loud about it?
It is effective. And I think they were in the tradition, this is called reflection. There have been a lot of studies showing that if you can get people to reflect, it's good. The hard part is getting them to reflect. If you ask students to, at the end of a problem-solving session, reflect on that. Ask me questions about the stuff you found hard and so forth. They basically shrug and say, yeah, I did well, and you say, well, that's not enough detail. Tell me how it worked. How did it go through your mind? They say, well, first I applied the distance rate time equation. Then I applied this other equation, and that went pretty well. So then they just give you a verbal report of their physical behaviors. So the hard part is getting people to sort of dig in and think about their thinking. I'm not an expert on that, but that's what I understand.
So it seems, and this makes a lot of sense, that the way that you approach this is to find a tutoring system that kind of enforced this behavior on them. That you need to fill the slots, and then when that was enough, you need to fill the slots specifically that are the correct, and then you slowly introduce the fuzziness to it. Is there a way to reverse the process, or have you looked into a way to reverse the process where instead of enforcing it when they're solving, the system can say, oh, I noticed that you might have made this mistake, or noticed that you might not have filled the slots correctly or something?
Yes, I know exactly the kind of system you're referring to, and it's there have been attempts to build such tutoring systems. The one I'm familiar with was done by Pam Jordan and her team, and the basic idea is they start by assuming the competence, like you said, and if the student is not competent enough, then they sort of ratchet down the amount that's expected to them and ratchet up the amount of help they're given involuntarily, like our scaffolding. Don't really know how that came out. I would expect it came out pretty well. The hard part is engineering it. A lot of these scaffolds that we build are built by giving them a user interface. So you're asking them to switch from one user interface to another. That in itself is a barrier. So the tricky part is how to have scaffolding that is done all within the same user interface. That's the hard part. Now, in Pam's case, she was working in a natural language tutoring system. Really easy. The interface is always the same as natural language. So it's easy to increase the amount of scaffolding.
Thanks, Kurt. That was great. I know you didn't talk about fading, but I was wondering whether you could just give us a few thoughts on how noise tolerant fading is, how many observations and things you need to get before you can get a good fading strategy. I sort of tuned into that literature about a decade ago and haven't been there since. And so I'm just curious where the state of the art is.
I think you're up to date. I haven't seen any recent work on that. There was demonstrations that it worked, and then it just became part of the toolkit. So I can add one thing to that, which is it's not exactly fading, but it's along the same lines. In fact, it ties in with the talk that we heard, saw earlier about task difficulty curriculums. A lot of tutoring systems will work by basically dividing up the problem sets into, as that paper did, into sets of equal difficulty and equal sets of knowledge required for them. And then when you reach mastery on one of those sets, then you get a little lesson on the next piece of knowledge you need to know, and then you get another set. And when you reach mastery on that, so forth. So the way this is operationalized in things like mastering physics or many other, or ALEX, the one we use in math classes at ASU, is mastery means achieving a greater percentage of problems correct than incorrect. The problem with that is it can't differentiate between, because it's an answer-based system, it's only looking at the answers, not the steps required to achieve them. It can't tell the difference between an answer that was made with a little tiny mistake, an unintentional mistake somewhere in the derivation, versus one which is incorrect because the person is lacking knowledge. Because of that, people make one little slip and it increases the number of incorrects they have. So they might go from, say, 3 incorrect and 15 correct, which is almost at threshold, to 4 incorrect and 15 correct, which is way below threshold. And so they have to do a lot more corrects to get it back up. And they hate it. They absolutely hate it. So that's another reason why I like step-based tutoring systems. It can often make the distinction between unintentional and intentional errors.
Great talk. Thank you. So I know that throughout your career, you've been focused on these applied problems in mathematics learning. And the studies you've done, the systems you built reveal a lot about both human problem solving and learning in those settings. But of course, we're also interested in more general theories of cognition and learning. And I'm wondering if you could just make some conjectures about how much this would carry over to other settings, other procedural domains, things like driving, or how much does it carry over and how much of it is really specific to mathematics and physics problem solving, things like that. I won't request any evidence right now.
Okay. Once I was assembling a barbecue grill, which came in a big box, and it had a lot of bolts and things that you had to attach in various locations. And so I'm attaching these bolts to the body of the curved body of the barbecue grill to its legs, and it's really difficult. And I finally figured out a trick. And the next time I had to do the same thing a few minutes later, I had to kind of think for a minute to recall the trick, kind of muffed it a little bit, then got it right. The third time it went smoothly, and the fourth time it was getting faster. So that's me learning from exactly what my subjects in math learned. They hit a time when they had to have a new piece of knowledge and they didn't have it, and they struggled, they found it. Then they have to struggle again a little bit the second time. The third time, it's basically a memory thing. And the fourth and the fifth time, the memory is stronger. There are fewer fumbles and unintentional mistakes. So that's the story on all human learning. There's famous learning curves. They show this log or exponential decay in the amount of time and the number of errors. But the part that's most interesting is that first part where it's really high. That's where the people are sort of discovering little tricks, discovering things and figuring it out, and then having perhaps to refigure it out and then finally getting it. Okay, so in driving, so if I was driving here, there would be a lot of tricks I would have to learn, especially about how to go through an intersection when there's no traffic lights. That would be a new set of learning things for me. So yes, I think it does apply.
Any other question? Okay, thank you.
Thank you very much.
And now on to the next announcement. So, like his predecessors, the recipient of the 2024 Simon Prize is a senior researcher who throughout his career has taken a cognitive systems approach to understanding the nature of the mind. In other words, he's been committed to the study of high-level cognition, structured representations, system-level research, heuristic methods, and links to human cognition. Recurring theme in his work is one dear to my own heart. That's that although people operate in continuous physical environments, they often represent and reason about the world in qualitative terms. He's also developed systems that learn from experience, but always ones that acquire rich cognitive structures, which are then used to support complex behavior. But I've beaten around the bush enough, so let me get to the point. I'm delighted to announce that the recipient of the 2024 Herbert A. Simon Prize for Advances in Cognitive Systems is Benjamin Kuipers for his contributions to representation, reasoning, and learning about navigational space, qualitative reasoning about dynamics, and cognitive development in robotic systems. Not yet, Ben. I'm still going to say a few more things. No, you can come back. You can come back. That's okay. So Ben received his PhD from the MIT AI lab in 1977, where he worked with Marvin Minsky, a thesis titled Representing Knowledge of Large-Scale Space. Served as professor of mathematics at Tufts from 1977 to 1985. Then he moved to the computer science department at UT Austin, where he remained through 2008 when he took a faculty position in computer science and engineering at the University of Michigan, where he remains to this day. As I mentioned, Ben's done groundbreaking and influential work on qualitative reasoning, spatial cognition, and map learning, with much of his research inspired by results from psychology. And like Kurt VanLehn, he's even published analyses of verbal protocols collected from humans. Most recently, he's turned his attention to ethics in AI and robotics, a topic of growing importance. So now let me give the floor to Ben. I hope he'll make a few comments and tell us more about his work in his talk at the next ACS meeting.
Well, thank you very much, Pat. I'm deeply honored to be the next recipient of a prize in honor of Herb Simon, who I have known and respected for many, many years, and to join the amazing, wonderful people who have been the previous recipients of this prize. I think you've done a nice job of capturing my focus on understanding the nature of the mind. And when I came to MIT as a graduate student, I was going into pure math, and I was going to be as pure as the driven snow and never do anything applied. And then I stumbled across Minsky and Pappert's Graduate Introduction to AI, and I realized that this had the promise of providing a mathematics that was adequate for describing the mind. We weren't all the way there, but we had a bunch of the ingredients, and over the following decades, we've accumulated a bunch more of the ingredients. We're still not there, but we're making really interesting progress. I have defined my focus as common sense knowledge and started with a focus on common sense knowledge of space, particularly navigational or large scale space. But I've always been interested in space as a foundation for many other kinds of knowledge. But once I reached a sort of plateau on that work, I started getting very excited about the work on qualitative reasoning about physical systems. And it's clear people have common sense knowledge about how systems work, even though they don't completely understand the model. And so that's been very exciting. And each time I get attracted to another aspect of common sense knowledge, these provide the foundation for many other kinds of reasoning. In Kurt's talk, the spatial structure of that scenario provides a simplified foundation on which everything else can be built. If you tried to include everything in the world, it simply wouldn't be tractable at all. So, in fact, in my recent work in ethics, I also consider that to be a kind of common sense knowledge about the social world, what's okay to do. And it also raises many of the same kinds of issues. But I very much look forward to talking about this at your next conference. And I'm very grateful for this award. Thank you very much.